For a load impedance ZL equals 40 plus J30 ohms, determine the apparent real and reactive power in the circuit for source voltage of 120 volts. We're asked to do that using 5 different methods for computing real and reactive and apparent power. So given all the stuff up here, ZL is equal to 40 plus J30. It's supposed to be a plus sign there. Vs is equal to 120 angle 0. It's the reference voltage. Given those formulas, find S, P, and Q, apparent, real, and reactive power. So part A says that S is equal to I star V, where star represents complex conjugate. It means just take the inverse of the angle only. So to do that, we need to know what the current is, and we know that from Ohm's law, I is equal to V over Z. That works in vector format, so we've got 120 angle 0 degrees over 40 plus J30 ohms. That gives us a current of 2.4 at an angle of negative 36.87 degrees amps. It's always good to check. We know that the current angle is opposite that of the impedance. So we've got an inductive impedance here. That means we got a lagging current. So that's good. We can then use this formula here to calculate apparent power. That's going to be 2.4 at an angle of plus 36.87, accounting for the complex conjugate of the current, and then we just need to multiply that by 120 at angle 0 degrees. We get a apparent power of 288 at an angle of 36.87 degrees. Remember that this is in units of voltamps. So the magnitude of the apparent power is 288 voltamps. That's probably the most common way that apparent power is cited, is by just stating, but by repressing the angle. P is going to be 288 times the cosine of 36.87 degrees. That gives me 230.4 watts, so it's a positive number. That's always a good sign. Q is going to be 288 times the sine of 36.87 degrees. That's going to give me 172.8 var. I know that it was an inductor and my var is positive, so we know vars consume power. We're on track there. So that was A using I star V. All the rest of these formula are based off of this formula, just using substitutions of Ohm's law. Just plug that in there. And so we know I complex conjugate is V over Z star, which is just equal to V star over Z star. And the other thing is that a V star or I star, IR star, whatever, is always just going to be equal to the magnitude of the quantity squared, since the angles will cancel out. So we've got those calculations to do. So for B, we've got S is equal to the magnitude of V squared over the complex conjugate of the impedance. So that's just going to be 120 squared. The impedance was given to us in rectangular form. An easy way to put rectangular form to take the complex conjugate of it is just going to be 40 minus J30. So that's J star there. And so that's going to give me 230.4 plus J 172.8, where that's watts and that's bars. So if I get the same numbers here as I did for A, I know that I'm going to get the same impedance, or not impedance, I'm going to get the same apparent power, so I'm not going to do that calculation. So moving on. C, we were asked to use S is equal to the magnitude of I squared Z. So we know that from our calculation earlier that the current was 2.4 at an angle of negative 36.87 degrees. So the magnitude of that is just 2.4 amps. Now we just need to multiply by Z, 40 plus J 30. And again, we get 230.4 plus J 172.8. This worked for us because these are in series, so they have the same current through them. Part D asked us to use the formula S is equal to magnitude of I squared times R plus J magnitude of I squared times X. So that's going to be equal to 2.4 squared times 40 plus J times 2.4 squared times 30. You can see that this formulation is exactly the same as this. It's just the 2.4 has been distributed out, so it's no different there. And we get 230.4 plus J 172.8. And it's okay to write your power like that, just that whole unit is volt amps. Finally, in E, we were asked to solve using S is equal to the magnitude of V squared over R plus J times the magnitude of V squared over X. This one's a little tricky because the voltage that we were given is not the voltage associated with R and not the voltage associated with X. Instead, it was the voltage associated with those two in parallel. So we've got this situation. So we need to know, to use this formula, we need to know what VR is, and we need to know what the voltage across the inductor is. Fortunately, there's just two elements, so we can just easily use the voltage divider formulation. We know that the voltage associated with the resistor is just going to be, excuse me, 120 times the ratio of VR to total circuit impedance, which is just 40 over 40 plus J30. So we know that the voltage across that resistor is going to be 96 at an angle of negative 36.87 degrees volts. And we can solve for the inductor just by doing 120 minus that, or we could also do a voltage divider where we've got 120 times J30 over 40 plus J30. So that times that divided by total circuit impedance, that's going to give me 72 at an angle of 53.13 degrees volts. If you add those two together, you should get 120 at 0 degrees. And so now we can solve for S. That's going to be equal to 96 squared, which is the magnitude of the voltage across the resistor, divided by the resistance of 40 ohms, plus J times 72 squared, which is the magnitude of the voltage across the inductor, divided by the inductance, which is 30 right there, or the inductive reactance, which is 30 right there. And we get 230.4 plus J 172.8, again, volt amps. So this problem really illustrates that when you're calculating S, you can use the same rules that you already know for power, P, when you're looking at purely resistor circuits, but you have to be careful about making sure that you're using I and V actually associated with the components that you're interested in calculating the apparent power for.